Let's continue our discussion next with this corollary. It's a corollary to the proposition that we saw in the last analysis video. And in this corollary again we have a metric space x comma d in which there is a subset E. So that means E is a subset of X. Then the closure of E equals the interior of E union the boundary of E, and that is also equal to the complement of the exterior of E in X. Because the proof is not available in the text, so we have to see the proof. Actually this part we have already seen in the previous video, we discussed. From the equivalence of parts A and B of proposition 12 to 10, we get this, the first equality. What was part A of this proposition? Namely that X is an adherent point of E. X is some point in the space X. X is an adherent point of E. And part B was this statement, X is either an interior point of E or it's a boundary point of E. So obviously this is true because A and B are equivalent to each other. And next we have to also see how this is equal to this. And that second identity is also very easy. You first note this fact that the entire space is equal to the interior of E union the exterior of E union the boundary of E. Why? Because if you take any point of this space, then that point is either an interior point of E or an exterior point of E, or if none of these two is true, then by definition it's the boundary point of E. That is why anything here is automatically in this union, and this union of course is also contained in this because these are after all subsets of X. And additionally these sets are mutually disjoint, no two of them intersect. That is why the union of this one and this one will be the complement of this third one in X. That's it. And next we are going to define finally open and closed sets in a metric space based on the notion of boundary points in this definition 12 to 12. So let X comma D be a metric space and E be a subset of X. We say that E is open in X if E contains none of its boundary points. So let's continue the definition. So what did we say just now? That E is said to be open if E contains none of its boundary points, i.e. if this condition is true, namely that the boundary of E and E do not intersect. So this is one extreme, and the other extreme gives us closed sets. We say that E is closed in X if E contains all of its boundary points. That is, in this case, the entire boundary is contained inside E. So you get the thing here. E is open if E contains none of its boundary points. That is, if this condition is true. Whereas E is closed if E contains all of its boundary points inside of it. That is, if this condition is true. So in between these two extremes also we may have cases. You may have a set in a metric space which contains some of its boundary points but does not contain the others. That is also possible. So by this definition, such sets will be neither open nor closed. So we complete writing the definition. If E contains some of its boundary points but not others, then E is neither open nor closed. So let's take a concrete example to understand these things. This example, in which we take our familiar space of real numbers with the usual standard metric D, and we consider this open interval 1, 2 in place of E. This is an open set. Why? Because it has these 2 points as its boundary points, 1 and 2, none of which belongs to this. That is why by definition this is open. If we instead consider this closed interval in R, then this is a closed set, because just like this open interval, this closed interval also has the boundary points 1 and 2. Here, however, both of them belong to the set. That is why it is closed by definition. And finally, we consider this set, this half open interval 1, 2. This set is neither open nor closed, because just like those two intervals, the boundary of this interval is also, it's this two element set which has 1 and 2. 1 belongs to the set, but 2 does not belong to the set. Why is this set not open? In order for a set to be open, it should not contain any boundary point. 1, however, is there inside, that is why it's not open. Why is it not closed? For a set to be closed, all of its boundary points have to be inside the set. 2 is a boundary point, but it is not there inside the set, so it is not closed either. Now, besides having sets in a metric space which are neither open nor closed, we can also have sets which are both open and closed, and this next remark is about that. Let us first see in what condition that is possible. So again, you take a metric space X, D in which E is a subset. Suppose the boundary of E is empty. We have already seen such examples. I will remind you of exactly what I am talking about later. But let us first consider this condition. If the boundary of E is empty, then obviously it does not intersect E because it's empty. If you intersect any set with the empty set, you get the empty set. So this condition tells us that E is open. But at the same time, the empty set is a subset of every set. So this other condition is also true. And that is why E is simultaneously closed. So such sets which are both open as well as closed have a name. They are called Clopen sets. Now this is only one condition, theoretical. Can we produce an actual example of Clopen sets? Let's see. So here is an example. You may say that it is not concrete, but it's just general. So in our general metric space X, in place of X you can consider any concrete metric space. You consider the subset E which is X itself. Okay, what about X? You take any point X in X and any positive real number R and consider the ball centered at X having radius R. This set by definition is a subset of X. So by the definition of interior point, X becomes an interior point of X. Of X I should have written, but you understand that here we are talking about this X itself as our subset. What does this mean? It means that every point of X is an interior point of X. So a point is either an interior point or an exterior point or a boundary point. Because all points are interior points, obviously there is no boundary point. That is why the boundary of X is empty. And by what we discussed just now, X is Clopen. X is both closed as well as open. So this is one Clopen set which is present in every metric space, namely the entire set itself. There is another one. Next, you consider this case. This time E is the empty set. The empty set is also a subset of X. Here also we take any point X in X and we take any positive real number R and consider the ball centered at X having radius R. What is its intersection with the empty set? Empty. So by the definition of exterior points this time, X is an exterior point of this E. So every point in the space is an exterior point of the empty set. So no room for boundary point. So here also the boundary of the empty set remains empty, and that is why the empty set is also Clopen. It is both closed as well as open. Are these the only examples of Clopen sets in a metric space? Not necessarily. There are metric spaces where these are the only Klopen sets and they are connected. We are not going to talk about connected spaces now itself. In a sense, connected spaces are in one piece. They are not broken. But you can have broken spaces, that is spaces where besides these Klopen sets which are always present, there are others. Let me now remind you of that example that I said just now. We have already encountered this, where there is an overabundance of such sets which are Klopen. All subsets are Klopen. And that example is this: the set of real numbers with the discrete metric. Recall that we showed that no matter whatever subset E we choose in this space, its boundary is empty. So that is why any subset is Klopen, both closed as well as open. It's a very extreme metric space in the sense that it is as broken as things can get. It is discrete, not continuous. I am not using these words as technical words, okay, just you kind of understand what I mean by these words. A discrete space is like a collection of points, like for example the set of integers, where things are a little apart. They are not really very close together, parts of the space, whereas a continuum is a space where things are very closely packed together. There is a continuity. Okay, these remarks are vague, but you get the point. So this is a very that type of space, as we have the integers. And finally we come to proposition 12 to 15, the last result of this section. Here there are several parts and all of them are about properties of open and closed sets. But before we see the parts, let us focus a little on the words open and closed themselves. Usually when we say that something is open or closed, we mean that it's exactly one of these two. A door is either open or closed. It cannot be neither or both. Sets in a metric space, however, are not like that. Some of them are open and not closed, some of them are closed and not open, some of them are both, some of them are neither. So you should not really use these words in the usual literal sense when you are talking about openness or closedness of sets in a metric space. These are technical words. Okay. Now let's see the parts of this proposition. So obviously it's about a metric space. So let's take any metric space x comma d, and this is part A. Let E be a subset of X, and this part is about openness of E. Then E is open if and only if every point of E is an interior point of E, i.e. if and only if E is equal to its own interior. That means this is what you have to prove. If E is open, and conversely, if this is true, then E will be open. That also you have to prove because it's an if and only if statement. Now let me remind you of something that we have already seen when we defined interior of E. How did things start? Things started by defining interior points. You have your space X, you have your subset E, a point say y, okay, small y of X is said to be an interior point of E if there exists a positive real number R such that the ball centered at Y having radius R is entirely contained inside E as a subset. And from this definition, back then we also noticed the fact that y as a result itself has to be inside E. In other words, we noticed that every interior point of E is after all inside E. So, in showing that this equality is true if E is open, already one containment is with us, namely that the interior of E is a subset of E, because every interior point is already inside E. So, if you are going to show based on the hypothesis that E is open, that this is equal to this, you just have to show that E is also a subset of this. We will go through these details when we actually prove this result. But let's see the other parts. Just like openness of a set is connected to interior points or to the interior of the set, closedness of a set is connected to adherent points of it. E is closed if and only if E contains all of its adherent points. The set of adherent points by definition is the closure, which we denote by E bar. So that means all the adherent points being inside E is equivalent to this, that the closure is a subset of E. Now something else can also be said here. Next we are going to see that which involves convergent sequences. And that other equivalent statement is this. I was foolishly trying to confine myself to this part only, but I ran out of space. So I decided to use that part. E is closed, IWF means if and only if, for every convergent sequence xn in E. What does that mean? It means that all the terms xn of this sequence are points in E. And the sequence being convergent means that there is a point, some point x in X in our original space to which it converges. Then that X, which is this limit, is also inside E. That is, no matter whatever sequence of points in E you choose, if it is convergent, then the limit, that is the point to which that sequence converges, will be inside E itself, it won't be outside E, if E is closed. Conversely, if this property is what E has, then E will be closed. Next we have part C. In part C, you take any point x0 in X and any positive real number r and consider the ball centered at x0 having this r as its radius. Then this ball, which basically is just a subset of X, is open, and that is why sometimes these balls are also called open balls. I mean, in their definition itself, this word open, you will see it elsewhere. They are called open balls. In this book, however, they are being called balls, and now it is being revealed that they are open sets. Part C is about something else also. Along with this, we have this thing. Let us first recall the definition of this ball, open ball. It is the set of those points x in X such that the distance between X and this center x0 is less than r. And this idea comes from disk in your ordinary two-dimensional plane, less than r. But if you make that less than r less than or equal to r, then you similarly get this other set. This one is the set of all points x in X such that the distance between X and x0 is less than or equal to r. So when you consider this set with the possibility of the distances being equal to r, then it becomes a closed set. And because of this, some people call these sets, this set in particular, the closed ball centered at x0 having radius r. It's like that disk along with its boundary, which is the circle, not just its interior. Then we have part D, which looks very simple. If you take any point x0 in X, then the singleton set consisting of x0 is closed. There are some spaces more general than metric spaces. They are called topological spaces. In a general topological space, also there are open and closed sets. This property is not necessarily true in all topological spaces. Spaces which have this property, for example metric spaces, are special. Next we have part E. Let E be a subset of X, then E is open if and only if the complement of E in X is closed. So this is the relationship between open sets and closed sets. It's not like doors. We have already said this, that when a door is open it is not closed. The relation is not like that here. A set is open if and only if its complement is closed. When at one point we will define topological spaces, here itself, I mean in this book, this will become the definition of our closed sets. I think so, yes. This is how we define closed sets in a topological space. Next we have part F, in which we consider finitely many open sets in X. The number n can be very large, it is just a positive integer, and you take their intersection, then the intersection will also be open. In other words, the intersection of finitely many open sets is open. Now if you take finitely many closed sets f1, f2 up to fn, then their union is closed. These things can very quickly become confusing. Okay, so unless you see the proofs, there is really no point trying to memorize these things blindly. Next part G. Instead of a finite family of open sets, say you have an arbitrary family of open sets. This may also be finite, but it may be infinite also, of any cardinality. Say indexed by some set capital I, and the index is alpha. What that simply means is that for each alpha in I, you have an open set E alpha in X. Then this time we are considering their union, arbitrary union of all these E alphas. Then that is open. Do you see the source of confusion? When you are considering finitely many open sets, you are taking their intersection. Not that you cannot consider their union. In fact, that is what we are doing here. If this is a finite family of open sets, then this union will also be a finite union like this one. That is open, but when you are considering any family of open sets, finite, infinite, anything, then their union is open. However, when you consider intersection, then only finitely many open sets are considered, because there are cases where you can take an infinite family of open sets, but their intersection is not open. Okay, but anyway, this is what we have about arbitrary family of open sets. Their union is open. Similarly, you understand that one having closed sets is coming. So next we are similarly considering any family of closed sets in X this time, but a non-empty family, because we are now going to consider their intersection. And when you have the empty collection considered as a collection of sets, and you forcefully try to consider its intersection, a logical problem arises. But anyway, not going into those things. So it's the non-empty family of closed sets. That means there is at least one closed set. For each alpha in I, there is a closed set F alpha which is closed in X. Then the intersection of all these closed sets is closed. We can express this entire thing, this part G, like this. An arbitrary union of open sets is open, and an arbitrary intersection of closed sets is closed. And we can express the previous part like this. A finite intersection of open sets is open, and a finite union of closed sets is closed. And finally, there is one more part. And in this final part H, again we are considering a subset E of X. Then it's not about openness or non-openness of E. We are not talking about that. We are talking about the interior of E itself. This set is the largest open set contained in E. That's the statement. Now let's try to understand what that means. This is the largest open set. Let us first focus on the words open set. This means that interior of E as a subset itself is open always, and it is the largest such set contained in E. We already know that interior of E is contained in E as a subset. This we knew even before defining open sets and these things. But it's the largest open set that is contained inside E. So next we write that is interior of E is open, and if you encounter possibly another open set, say V, which is also inside E, which is contained in E, then this V should itself be contained inside the interior. In that sense it is largest. It contains all other open sets which themselves are contained inside E. Largest in the sense of this inclusion relation. On the other hand, the closure of E, E bar is the smallest closed set containing E. That means E bar as a set is closed. First of all, we have that. And the second thing is that E bar contains E. And the third thing is that it's the smallest such set, which means that if K is another closed set containing E, which may or may not be equal to E bar itself, then K contains E bar. In that sense, E bar is the smallest. Now that part which tells us that an arbitrary union of open sets is open, and the one before that which tells that a finite intersection of open sets is open. These two properties, and also the fact that the entire space and the empty set are both open, these are taken as the starting point of topology. And the section ends here. After this, of course, we have exercises where we are mostly going to solve this. Solve this means prove these things that we have left unproved here. So in the next analysis video, we will start solving the exercises. So see you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.